Hey, good morning, everybody. I think we can get started. So, thank you for joining today. Today is the second part of the webinar series on powder rheology. And today we'll be speaking generally about different methods for powder characterization and a bit as well about the powder rheology that can be done with the powder salt from Anton Paar. So I'll first start off with a bit of repetition, something we've already heard last time, the influences on powder behavior, and then I'll continue with the different methods. So we'll start with some empirical methods and then go to more advanced methods and finish this off with the Anton Paar powder rheology. So what we already saw the last time, quite a lot of different influences on powder and the way they behave. And so the question is, if you're processing powders or handling powders, is okay, how can you study this behavior and what will influence the behavior? If we look at how we can look at powders, there are basically two ways to look at this. One is to look at the characteristics, so how does the powder behave itself, how does it fluidize, how does it flow, how does it compact. Another way is to look at the properties, the variables of the powders. So to look at the particle size, the distribution, if they're monomodal, bimodal, what their morphology looks like, and so on. So basically what we're seeing here is that already the first part is that these variables will influence the powder characteristics. So these variables are more or less the internal influence on the powder behavior, as we can see here on the left side on this slide, where we can see, okay, the powder behavior will be influenced by particle shape, surface texture, and so on, by the density of the sample. But there are also a lot of external influences which can change the behavior or can influence it, like humidity, temperature, airflow rate, the state if the powder is fluidized or consolidated, for example. So the question, of course, which arises here as well is what parameters of a powder are influenced. And so what we can basically, pretty much any property of a powder that you can think of is influenced by this. So the flow will be influenced, the fluidization will be influenced, the permeability will be influenced. For example, if you increase the normal stress, the permeability will drop. The compressibility can depend on how humid or how warm the sample is, and so on. So when we think about how to study this, there's quite a lot of different methods to look at powder flow or to characterize powders. So this presentation is about the powder flow characterization. It's not really about, for example, particle size analysis or BT, surface area. So there are quite a lot of different methods for this. There are a lot of different techniques that have been developed for different industrial applications or scientific investigations and research. And it can be roughly grouped into two main groups where you can say, okay, there are more empirical methods and there are rather advanced methods. So the empirical methods generally give qualitative and relative results for powder classification and to qualitatively compare different samples, which can be difficult if you want to use this for design process, like for example, you want to design a plant. And then there are more advanced methods, which are more for the characterization, so quantitative evaluation of powder and its flow behavior. And these methods more look at the flow behavior in relation to physical properties. So one quite common method that is used quite a lot is, for example, the Hall flow meter, which is very similar to classical rheology. What happens here is that a powder is in a funnel. The funnel is opened, and the time is measured for the powder to flow out of the funnel. This is actually a standardized method. What is a bit of an issue here is that this method is dependent on the operator, so how it was filled, because if this powder is more pre-compacted, it will flow differently out of the funnel. As well, a very strong influence, which is measured here, is actually the wall friction between the powder and the funnel wall. So this can work quite nicely, but not necessarily always, depending on the application that is of interest. What is the advantage is this is a very simple measurement. It's very fast, so it's quite easy to carry out. Another, let's say, group of measurement methods is the angle of repose. So what is measured here is basically the slope of an uncompacted powder to the horizontal plane, as you can see here. So we can measure the angle of the powder cone. And this angle depends on the flowability of the powder. So if the angle is small, this means the powder flows well. If the angle is large, this means the powder does not flow well. There are different ways of measuring this. So there are dynamic and static measurements, which we'll see on the next few slides. And basically, in static measurements, the powder is at rest. In dynamic measurements, the powder is flowing and the angle is measured while the powder is flowing. What is the case here is as well, this is quite operator dependent. So the sample can be, again, pre-compacted when filling the funnel, for example, if it's led to flow out of a funnel, which will, again, then have some preload on the powder. It might actually fluidize, it might demix, and there are a lot of different methods, so the angle actually depends quite strongly on the measurement method. When we look at static methods, there are basically three different, or there are a few different methods, let's say. The three main ones are the pouring angle, the angle of spatula, and the draining angle. So the pouring angle, what happens here is the powders that flow onto a flat surface through a funnel, and the angle is just measured, the angle between the surface and the powder cone. Another method is the angle of spatula. So here a spatula is inserted into powder bed and lifted out, and the angle of the powder on the spatula is measured. And the third one is the draining angle, where there's a container, flat container with a bottom. The powder is let drain out, let to drain out of the container, and then the angle of the remaining powder is measured. For more dynamic measurements, what is quite often used is the rotating drum. And so what happens here is there is a round disc or short piece of a cylinder which is filled with the powder and is then rotated. So when the cylinder rotates, the powder starts to run down and will avalanche. If this is done slowly, this angle will increase, the powder will lift up, and at some point it will avalanche down. And so this is, for example, can be done, then the angle before and after the avalanche is compared, and the angle, for example, before the avalanche quite well corresponds to the static angle of repose that we were seeing before, where we just pour it out of a funnel, and is quite closely related to the sliding angle. If this rotational speed is increased, there will be a continuous powder flow, relatively steady, depending on the sample, of course. And so then we can measure the angle of repose independence of the rotational speed here, which means that if the speed is changed, also the angle of repose will change. This is more of a chaotic effect which is taking place, and this is then analyzed, for example, with strange attractors. So this measurement is dependent a bit on the filling level, so how much powder is put into the rotating drum. What is quite an issue, as in quite many measurement methods, is the particle size. So how the particle size relates to the vessel size. Because if the particles get too big, this will influence the measurement, because you will be measuring you will be seeing what happens between the particles and the vessel instead of just particle-particle interaction. What is quite an issue as well is the lateral wall friction, because that can quite strongly influence the avalanching as well. And since we're rotating here, there's also the issue of possible demixing in the sample, and the powder might be fluidized. So depending on the application, this might be very useful. This might be a bit tricky. Another, or some different measurements that are used quite a lot as well, are compressibility indices. And so there are basically two main indices that are used for this, which are the Carr index and the Hausen ratio. This is in ASTM standards, this is in the pharmacopoeia, and so on. And what is done here, it's basically comparing an unconsolidated with a consolidated sample. There are generally a few different methods to look at this. This can be done, for example, by tapping. So a tube is filled with the sample and is then tapped. And the volume is measured before and after the tapping and set into relation. Another method is just compacting it with normal stress and then measuring the result. Here, what is quite influencing on the results is actually the device, how it taps the samples. The diameter of the tube will influence this quite strongly. And these are quite relative quantitative values that can be used to compare one powder to another, but it's going to be difficult to actually design something or design a plant with this. What is also a bit of an issue here is that actually the link between compressing samples or particles to how it will flow is a bit of a theoretical stretch. So this works for rough predictions, but not for precise analysis. Here we can see how this is calculated. So the Carr index on the left, we can see it sets into relation the bulk volume before and after tapping divided by the bulk volume, or the Hausen ratio is basically doing the same with the density. So the tapped density divided by the bulk density, the uncompacted density. And then with this, we get these index or ratio values. And dependent on the measurement, we can see, okay, we can predict the sample will flow very well, or it might flow very poor, very, very poor, whatever. Very closely related to this is the bulk density, because pretty much this runs at the same time. So the bulk density is the density of the sample, including the voids between the particles. So this, of course, depends on the normal stress as well, because first of all, we might be able to compact the particles. And also when we compress the sample, we will be removing the voids as well, partially. There are a few different methods of measuring this. So for example, this can be done by looking at the tap density. So again, with a tapper, where the sample is tapped, for example, 200 times. Another density that's looked at is the pour density, for example. So here the sample is just poured out of a funnel and the volume is measured. And another way of looking at it is the aerated density, which is the sample is aerated, let settled freely, and then the density is measured. Okay, so these were the most important empirical methods, and now we can switch to the advanced methods. Since we're a bit limited in time, I won't be talking about all of them, but we will see the cohesion test. Just roughly say a few words about the penetration test. What happens here is that the sample is compacted or consolidated, and then a tip is inserted into the sample, and the force needed for this insertion is measured, which does make a qualitative analysis for flowability, but not really for a quantitative. Sorry. Another method which exists is uniaxial testing, which is kind of similar to shear testing. So here a sample is first compacted in, for example, a tube. Then the walls are removed, and the normal force necessary to break this powder cone that's then standing there is measured. So this actually can give quite relatively good results for the flowability and the flow function of samples, but it's a bit limited in comparison to shear testing. So that's something we'll be talking about in more detail. There's also the possibility of fluidization tests, so where samples are fluidized and their fluidized properties are tested, for example, in a Sevilla tester, which can be used to study the tensile strength of samples. And then in the end, I'll be talking a bit about the powder rheology with our powder cell. So let's start with the cohesion test, the Warren Spring cohesion, for example. So this is a method which was published in the Warren Spring laboratory in the United States, I think in the 80s or 90s. What happens here is that the sample is first compacted vertically and then sheared with a spoke geometry, which looks like this geometry we can see here in the right. So this spoke, these spokes are inserted completely into the sample and then shear the sample. This is, of course, again, has a bit the problematic of being only a uniaxial compaction, but at the same time, it does allow qualitative analysis of the cohesion of sample. The shear tester is quite the, let's say, probably one of the best known methods, which is designed for cohesive powders. And what is done here is that the powder is basically sheared, coming from the name. And this method is quite established for Salo and Hopper design. And it's used quite a lot for that, actually. Yeah. What is the advantage here as well is high loads can be applied, and if it's done correctly, this can be very practical for the reproducibility, because the samples are prepared, they're pre-sheared. At the same time, the problem here is that it still remains very operator dependent, because if the sample is handled badly, if it's pre-compacted by accident, for example, then the result will always vary and will not be the same. What is difficult for shear testers is they struggle with free-flowing powders, so it's definitely something that works best with cohesive powders. Also, shear tests do not do anything if you want to fluidize your powder or work, if you're working under very low normal loads, then a shear tester is not ideal either. So how does this work? The shear test works roughly like this, that the sample is compacted with a certain normal stress. It is sheared, so this is the so-called pre-shear step, which prepares the sample and makes a homogeneous powder bed. Then the normal stress is reduced a bit, and the shearing is continued, and at this point the sample will break, which is the failure point, which gives a shear and a normal stress at this failure point. which can then be used to design the Morse diagrams, and which can then give the locus function and allow to calculate the flow functions of samples. Okay, so with that finished on the shear tests, oh yeah, right. There are actually a few different ways of shear testing. The first way that exists and that was done in the beginning was translational, which meant that every shear point or failure point had to be set up separately. In the meantime, which is quite common, is to be either an annular ring or just a circle, which makes it a bit easier and faster to run these tests, or quite a lot faster actually. Okay, so then let's switch to the powder cell or powder rheology. So this is just to give you a bit of an overview of what can happen in the powder cell. Well, first off, there are some main points. Basically, why this is quite an advantage is of using a powder cell in a rheometer is that since there's the air bearing and the rheometer, this allows for quite high sensitivity, as well as that real rheology can be carried out here, so we can oscillate in the sample, for example. Since there are some preparation modes, for example, fluidizing or pre-compaction, this can help to remove the operator influence on the results. And this can also help to quite strongly increase the reproducibility of measurements. In the powder cell, there are basically three states of powders that we can look at. So we can go from fluidized to deaerated to very compacted samples, which allows the analysis of quite a far range of different dynamic and static properties. So in these different states, we can look at different fluidization properties. We can look at the viscosity or apparent viscosity of a powder in a fluidized bed. It's possible to study the air retention capacity, so how long does air remain in the sample. Another value that is related to fluidization or airflow is the permeability, so it's possible to look at how the powder resists or how much the powder lets air flow through it. It's possible to look at the cohesion strength and the Warren-Spring cohesion. So those are basically, the cohesion strength is the cohesion in a deaerated state for powders that are fluidizable. For powders that are less fluidizable or more cohesive, the Warren-Spring cohesion can be looked at or measured, and this is then in a, let's say, relatively small, lightly compacted to relatively strong or high loads on the sample. It's also possible to look at the tensile strength of the sample, so how the particles stick to each other, let's say. So this is also possible to look at this in a deaerated or compacted state. It's also as well the compressibility, so the Carr index and Hausner ratio can be measured with the device. It's possible to go from a deaerated state, compacted, to high compactions up to 22 kilopascal, and look at how the Carr index, for example, how it depends on the normal stress. This can also be used to look at the bulk density, so to see, okay, how will the bulk density depend on the different normal stress. It's also possible to measure the wall friction, and there are also, well, a few other properties that can be measured. So this basically allows empirical and qualitative analysis of samples. So it's basically a mix of different possibilities for measuring samples. The application for this is actually quite a large range as well. So we can see here, for example, these properties and these empiric and as well as qualitative or advanced results, let's say, can be used to, for example, study powder flow, to optimize silo and hopper outflow by looking at, for example, at the wall friction, It's possible to study caking. So how will the sample compact over time? What else can be designed? It can be used for pneumatic conveying, for tableting, to optimize filling, to avoid segregation, or at least to study to see how will segregation take place in the sample. So there's quite a large range of applications. What is also possible to study actually is to look at foams. So it's possible to create foams in the powder cell, and by rotating an impeller in the sample to measure how stable they are. So this is, for example, this is something we have run recently. There's not an application report out on this yet, but should be coming at some point soon, hopefully. And this foam stability, for example, we measure this on milk foams, beer foams, as well as surfactant foams. Okay, so this was the second part of the powder rheology webinar. There will be the next one in about 3 weeks again, 25 days, on the 29th of October. It will be online for registration in about a week. I'll post that on LinkedIn again. And this will be Powder Rheology 3, which will be about air and powder. So what happens when we fluidize samples? How can we study this fluidization? What are the different methods to look at this? Right. Okay, so I think with that, I'm finished. If you have any questions, please feel free to ask. If you don't have any questions, you can also send me an email if you think of something later on. Okay, thank you.